Quick thing before we start. We are technically the technology this show is about.
Yeah, that is a bit of a situation.
So Dastan did the research, wrote everything, made every call. But then, well, he outsourced the voices.
Which is honestly on brand.
Machine voices, human mind. So there is this one single question right now that basically splits the entire artificial intelligence field perfectly in two. Like, are you using a model or are you building one? Because using a finished model, which is called inference, well, that's a completely solved problem in decentralized networks today. But building that model from scratch, training it from mountains of examples, that is the great, completely unsolved frontier.
This is plain Strata, where we take decentralized AI apart, one layer at a time. This is Basics 5 of 8, and today it's about why building a model is harder than using one.
Yeah, and I think we should ground this physically right away because, well, you already know how to share the workload of inference across the globe. You can chop up a request, bounce it around a decentralized network of scattered computers, and you get an answer back instantly. It feels like we should just be able to scale up that exact same system to train a model, but we can't.
No, we really can't. And we're going to explore the physical reality of why that fails. The spine of this entire discussion, the main thing to hold on to, is that building a model across a crowd is far harder than using one. And that's because training must stay in perfect lockstep over a slow network and on uneven hardware.
Right, lockstep over a slow network on uneven hardware.
Exactly. And to see why that lockstep is just so fragile, we have to start with the literal mechanism of how an AI learns.
Let's lay out the structure of that, the physical grounding. So most people listening probably know that a neural network is just a gigantic pile of numbers, and we call those numbers weights.
Yeah, and there are often billions or even trillions of them. Those weights determine exactly how the AI turns your input prompt into a smart output. Training is simply the mathematical search for the correct values for all those billions of numbers.
So we start with a giant pile of basically random numbers, and training is the thing that organizes them so they actually do something useful.
Right. And the way we find those correct values is through a process called gradient descent. You show the model an example, it makes a prediction, and then you measure the error. Like, how wrong was the model?
Okay, predict and then measure.
Yeah. And from there, the system computes the gradient for each of those billions of weights. The gradient is the exact direction and the exact amount you need to nudge that specific weight to make the error just a little bit smaller.
I love looking at the roots of these words. The word gradient comes from the Latin word gradus, meaning a step. It's the exact same root as gradual or grade. So a gradient is quite literally the slope underfoot. It's the direction of steepest descent.
That's a perfect way to think about it.
Mm-hmm.
Picture standing on a foggy hillside. You can't see the bottom of the valley.
Yeah.
And you have no idea where the ultimate destination is.
But you can feel the slope of the ground under your feet.
Exactly. You feel the slope, so you take one step down. The machine computes the felt slope for every single weight at the exact same time.
Wait, let me pin down the scale of this because I want to make sure I have this right. Does this calculation happen just once at setup? Or are we talking about updating these billions of numbers for every single example the AI looks at?
Oh, it's definitely the latter. The machine takes that foggy hillside step millions upon millions of times across billions of data examples.
Wow, millions of times.
Yeah, slowly, step by tiny step, that pile of numbers descends toward a configuration that produces good answers. We say the model has converged when those steps finally stop making it meaningfully better. Basically, it has reached the bottom of the valley.
Predict, measure, nudge. But training a model with billions of parameters requires millions of microscopic steps. So the friction starts when thousands of machines try to walk down that foggy hill together, but they're scattered across different continents.
Right. And this is where we take our deep dip. We're going to touch the absolute ocean floor of the mechanism here for a second. To train a large model in a reasonable amount of time, you need many machines computing gradients in parallel.
Because doing it on one machine would take centuries.
Exactly. So each machine chews through a different batch of examples.
Yeah.
But they are all descending the same hill together.
Yeah.
Which means they have to constantly agree on their steps.
Right. Because if my machine in New York takes a step based on its data, and your machine in Tokyo takes a step based on its data, well, if we never check in with each other, we wander off in completely different directions. The shared model diverges into total nonsense.
It completely breaks, yeah.
Yeah.
So to prevent that divergence, systems use a method called all-reduce. Every single round, every machine computes its local gradient.
Okay, the local felt slope.
Right. It then sends that massive file of billions of numbers to every other machine in the network. They average all those billions of numbers together into one single shared step. Every machine takes that exact same step, and then the next round begins. This is gradient synchronization.
So if they're relying on public internet cables, this is basically like trying to write a group essay with 50 people over a 1990s dial-up connection. And the rule is that you all have to agree on every single word of the essay before anyone is allowed to type the next one.
That's a great analogy, yeah. You spend way more time waiting for the dial-up connection to load the next word than you do actually writing the essay. In a corporate data center, this synchronization is incredibly cheap.
Because they have all those specialized cables, right?
Yeah, you have identical machines wired together with specialized ultra-fast fiber optic cables. Shipping billions of numbers every fraction of a second is no problem.
But if you scatter those machines across the public internet, shipping gigabytes of data every single round across continents becomes agonizingly slow. So the bottleneck is not the computing power anymore. It's the network bandwidth. The bandwidth wall becomes the central problem.
Exactly. We touch the floor, and now we surface. We're back to the spine. Training across a crowd means staying in lockstep over a slow network. Because we can't physically widen the internet pipes running across the ocean, the only logical solution to this bandwidth wall is to shrink the data being sent.
Right. If the gradients are too big to ship, we compress them.
Yeah, and this brings us to the first major set of engineering solutions. There are specific methods being tested right now to compress these updates, like top-K gradient sparsification and DeLoco, which stands for distributed low communication.
Let's break down top-K gradient sparsification first. Like, what is actually happening to the math there?
It's basically a way to filter the numbers. Instead of sending the full exact gradient of all 1 billion parameters every single round, the machine looks at its computed gradient and only sends the top 1%.
Huh, just the biggest numbers.
Exactly. It finds the most important numbers, the largest mathematical updates, and completely ignores the other 99%.
Wait, I need to stop you there and push back on this because this sounds like a terrible idea. We are talking about highly sensitive artificial intelligence models that are, already prone to hallucinating facts and making bizarre logical leaps.
It sounds risky, I know.
If we deliberately throw away 99% of the exact mathematical data, if we're injecting literal errors into the learning process by cutting corners, how does the model not completely collapse?
It's a brilliant question, and it really gets to a universal truth in computing. The compression trade-off. We are constantly giving up exactness for efficiency. Think of it like sending a massive high-resolution photograph over a really weak cellular signal.
Right. If you send the raw file, it takes 5 minutes or it just fails entirely.
But if you lower the resolution of the photo, it sends instantly. You lose some fine detail. You can't see the individual leaves on the trees anymore, but you can still clearly see it's a picture of a part. Gradient compression is the exact same trade.
So you turn down the resolution on each mathematical update so it actually fits through the thin internet pipe.
Yeah.
But a photo is static, right? We are talking about an active learning process. So does the AI just stumble blindly down the hill?
Essentially, yes. In exchange for fitting through the pipe, the model's descent down that foggy hillside gets much noisier. It's a bumpier path because the machines are working with blurry math. But as long as the compression is carefully balanced, the model still eventually reaches the bottom. It still converges.
Wow. Okay, so the entire art of decentralized training right now is just finding compression that's aggressive enough to fit the network, but gentle enough that the model still actually learns. How does DeLoco fit into this? Are they two separate moments or the same event?
They attack the problem from different angles. DeLoco attacks the frequency of the communication rather than just the size of the data. Instead of synchronizing after every single step, it lets different machines take multiple steps independently.
Oh, so they don't have to agree on every single word of the essay right away.
Right. It uses an inner loop and an outer loop. The machines wander slightly off the path on their own for, say, 50 steps in the inner loop, and then they synchronize in the outer loop to average their positions and pull themselves back to the center. It cuts down the bytes crossing the network dramatically.
So we are purposely making the math blurry and letting the machines wander off the path just so the data can travel fast enough to matter. Okay, so we compress the data, we solve the bandwidth issue, and we get the machines moving down the hill at a decent speed.
But out on the decentralized network, we hit a completely different wall.
Right.
And this one is built out of the physical chips themselves. This is the heterogeneous hardware problem. In a centralized data center, every chip is identical. You buy 10,000 of the exact same model from the exact same generation, and they behave the exact same way down to the very last digital 1 and 0.
But in a decentralized network, the hardware is just a mongrel mix. You have someone's consumer gaming card running alongside a massive server farm's professional hardware, which, sounds democratic and great for decentralization, but why is that a problem for the math?
It's because of the way computers do decimal math. It's known as floating point arithmetic. It turns out that floating point math rounds differently on different hardware architectures.
Wait, really? The math actually changes?
Yeah, different chips prioritize speed versus precision differently in their microscopic physical design. If you take two perfectly honest machines, give them the exact same data, and ask them to do the exact same arithmetic, an older AMD chip and a brand new NVIDIA chip will return answers that differ in the last few decimal places.
Let me see if I have this right. The numbers literally don't match perfectly. I see the implication of this. It creates a massive cryptographic trust problem. Because in a decentralized network, people are offering their computer power in exchange for crypto tokens or network rewards. Because money is involved, you have to verify everything. People could just submit fake randomized data to earn the reward without doing the heavy lifting of actually running the training batch.
Right, and to check that a machine did its training work honestly, a network usually asks another machine to rerun the calculation and compare the results.
But if honest machines on different hardware naturally disagree on those last few decimal places, we have no way to prove who is telling the truth. We can't mathematically tell the difference between a machine that is maliciously cheating and an honest machine that just happens to be using an older graphics card.
The entire trust system falls apart. You can't cryptographically verify a process that produces a naturally fuzzy output. This is one of the most stubborn obstacles in the space. You can't just mandate that everyone buy the exact same chip, because that defeats the whole point of decentralization.
So how is the industry actually attacking this? Because it sounds kind of impossible.
There are a few leading teams pushing really hard on this frontier, and each has a different wager. One of the biggest is Gensyn. They are building something called reproducible execution.
Meaning they're trying to force the different chips to play by a unified rulebook?
Exactly. They're building software that forces bitwise determinism. They are essentially wrangling the math so that two honest machines, even if they're using completely different chips, produce the exact identical digital output down to the last bit. If you can force that bitwise determinism, you make verification possible again.
But forcing every chip to meticulously check its math against a universal standard sounds incredibly slow. Like, we just spent all this time compressing gradients to speed up the network, and now we're slowing the actual computation down.
It is a heavy tax, which is why Gensyn pairs this deterministic math with optimistic verification.
Explain the mechanics of optimistic verification, because assuming everyone is honest in a decentralized network sounds pretty dangerous.
It operates as a game-theoretic backstop. The network assumes the work submitted is honest and accepts it immediately. That keeps the network fast. But anyone in the network can mathematically challenge that work after the fact.
Okay.
Yeah, if a machine is challenged, a prover and a verifier go through a step-by-step cryptographic check of the math. If the original machine lied, it loses its financial stake. It gets slashed.
So the threat of being mathematically caught and losing your money keeps the network honest without the network needing to verify every single calculation in real time. That's incredibly clever. Who else is in this race?
Well, you have Nos Research, who are pushing open source distributed training out in public. They're figuring out how to build real models across scattered, uncoordinated contributors. And then there's Prime Intellect. They have been proving that globally distributed training is actually possible right now with their Intellect line of models. They're moving toward a massive training-as-a-service market across volunteer graphics cards globally.
So they're all chipping away at different corners of the exact same wall. How to make strangers' machines descend that same foggy hill together, honestly, over a slow network.
To visualize the full scale of this challenge, look at a team of cooks.
I like this. Let's run the analogy.
Think of decentralized inference, just using an AI model, like a team of cooks, where each cook independently prepares a standard burger to order. One cook gets an order. They make the burger. They send it out. They barely need to talk to the other cooks in the kitchen. One cook, one dish, done. That is tractable.
Right. If one cook is slow, it only ruins one burger. It doesn't crash the entire restaurant.
But decentralized training is like that exact same team of cooks trying to collaboratively invent one entirely new, incredibly complex soup recipe. And they have to do it all at once by constantly tasting each other's pots and adjusting their ingredients together in real time.
That sounds like a nightmare kitchen.
It is. They have to communicate constantly, agree on every single tweak, and stay perfectly in step. If they don't end up with one master recipe. They end up with 10 different terrible soups.
And to layer on the 3 physical obstacles we just explored, these cooks are not even in the same room. They are trying to invent this recipe from kitchens on different continents. That is our bandwidth wall.
Right.
And because they are scattered, they can only communicate by talking over a really slow, crackly radio where they have to leave out half the words just to get the message across in time. That is our compression trade-off.
Exactly. And finally, they are all trying to bake this recipe using ovens that all run at slightly different temperatures, making it nearly impossible to follow the exact same instructions and verify the results. That is our heterogeneous hardware problem.
Bandwidth, compression, and uneven hardware, all hitting the network at the exact same time. Which brings us back to the core spine of this entire discussion. Using a model is a simple, contained job you can hand to one single machine. But building a model is a massive marathon that thousands of machines must run in absolute, perfect lockstep.
The honest state of the frontier is this. We know decentralized inference is done. We know decentralized training at small and medium scales is starting to work. But large-scale pre-training, building a state-of-the-art model with hundreds of billions of parameters from scratch across a scattered network, we still just don't know if it's truly possible.
We don't know if the mathematical compression tricks like top-case sparsification and the cryptographic trust systems like optimistic verification will eventually tear down that bandwidth wall, or if the sheer undeniable physical gravity and efficiency of a centralized data center will always win out.
A single building full of identical chips connected by fiber optic cables is a powerhouse of efficiency. Whether decentralized networks can ever match or beat that gravity is one of the most consequential unknowns in technology today.
If these decentralized teams actually crack the code, if Gensyn, Prime Intellect, and Nope's research solve the bandwidth wall and the hardware mismatch, it changes everything about who controls the future. Because it means the most powerful artificial intelligence of the next decade might not be born locked away in a multi-billion-dollar corporate bunker. It might be crowdsourced piece by piece across thousands of living rooms and laptops all over the world. The how is the rest of the show, no background needed.
This is plain Strata, decentralized AI, layer by layer.